All right, let's just dive right into this. Welcome to today's Explainer, where we are going on a journey from honestly kind of avoiding the terminal to absolutely mastering it. Listen, if you've ever felt a little intimidated by that blinking cursor, or maybe you rely pretty heavily on graphical interfaces that hide what's actually happening underneath, you are in exactly the right place. Today, we're cracking open the operating system that literally powers the internet. We're going to learn how to see it exactly the way a security professional and, more importantly, an attacker sees it.
So you might be wondering, why is this so absolutely crucial? Well, 96.3%. That is the percentage of the world's top 1 million web servers that run Linux. And it doesn't even stop there. 100% of the top supercomputers, all the major cloud providers like AWS and Azure, the routers securing your networks, the containers deploying your apps, they all run Linux. And attackers? Yeah, they know this. They aren't scared of the command line. They live in it. They move through these systems at blinding speeds, dropping backdoors and tweaking permissions, all from a plain terminal window. So if you're in cybersecurity, terminal fluency isn't just a nice-to-have skill anymore. It's completely non-negotiable.
So here's our roadmap for this explainer. First, we'll cover the substrate, then mapping the file system, core permissions, interrogating state, and finally, we'll wrap up with the defender's checklist. Let's get started.
Part 1. The substrate.
Before we even think about memorizing a bunch of commands, we have to understand the foundational philosophy of the Linux environment. The core concept of this entire system is actually incredibly simple. Everything is a file. In Linux, your hard drive, it's a file. A network socket actively transmitting data, that's a file. The hardware devices plugged into your machine, files. Literally, even a running process is represented as a file. This unified model is so powerful because it means the exact same commands you use to read a simple text document can also be used to investigate hardware or network activity. Once you really grasp that you're always just interacting with different types of files, the whole operating system suddenly just clicks and makes complete sense.
Part 2. Mapping the file system.
Think of the Linux directory structure like a massive tree. Everything branches out from a single root, which is just represented by a /. Now, I want to explicitly contrast how you, as a defender, view these directories versus what an attacker is actively hunting for. Take the etc directory, for example. You see system configuration files, but an attacker, they read etc to completely map out and understand the system's layout. Then there's /var/log, the system logs. To you, that's a total goldmine for forensics, but to an attacker, it's a massive liability that has to be cleared out to hide their tracks. And /root, that's the admin's home directory. If an attacker gets into /root, full compromise. It's game over.
But there is this one directory that attackers absolutely love, and that is /temp. It's the temporary files directory, sure, but the absolutely crucial point here is that it is world writable. Literally any user on the system can write data there. Because it has this universal access, it's the perfect, easy spot for an attacker to drop malware or execute malicious scripts. So when you're investigating a system, the /temp directory should always be one of the very first places you check for unexpected executables.
Part 3. Core permissions. Now, what's really interesting is the ultimate security gatekeeper in Linux. If you get this wrong, you expose the entire system. Take a string of characters like -rwx, rwx, rwx. When you run a basic command to list files, this is what pops up. It looks like total gibberish at first glance, right? But it's actually beautifully structured. It breaks down into 3 sets of permissions: the owner of the file, the group the file belongs to, and, finally, everyone else, the others. For each of those groups, the R stands for read, W stands for write, and X stands for execute. So if you ever see this exact string on a script, it means absolutely anyone can read, write, and execute it. And that is a massive security red flag.
To make managing these permissions a whole lot faster, Linux uses something called octal math. We just assign a number to each permission. Read is 4, write is 2, and execute is 1. You just add them together. So a 7 means 4 plus 2 plus 1, which equals read, write, and execute. Simple, right? How does this apply to the real world? Well, web server files are often set to 755. That means the owner can do everything, but everyone else can only read and execute. But think about something super sensitive, like SSH private keys. Those must be set to 600. The owner can read and write, that's the 6, but groups and others get a 0, absolutely no access. Actually, if you don't secure your SSH keys with 600, the system will literally refuse your connection because it knows it's just way too dangerous.
And hiding within these permissions is a really sneaky danger, the SUID bit, or set user ID.
This is a special permission that lets a program run temporarily with the file owner's privileges instead of the privileges of the person who actually ran the command. A perfectly normal example is the password change command. It temporarily needs root access just to save your new password. But as you can probably guess, this is a massive privilege escalation vector for attackers. They will actively hunt for vulnerable SUID binaries owned by the root user, exploit them, and boom, they instantly gain full root access to your machine.
Part 4. Interrogating state.
Okay, let's pivot the narrative a bit. We're moving from passive structure to live, active investigation. When you get called into a high-stress incident response scenario, this is the absolute high-stakes question you have to answer immediately. What is this system talking to right this exact second? We need to look at live network connections and running processes if we want to catch attackers in the act.
To get that answer, we rely on a few essential commands. The first one, SSTULPN, is just incredible. It instantly reveals all open, listening ports on your machine and tells you exactly which processes own them. It's basically the perfect tool to spot an attacker's backdoor connection. Then you have PSAUX, which lists every single running process on the system, letting you spot any malware that might be hoarding your CPU. If you do find something sketchy, you use LSOAuth with the process ID to see exactly which files that specific process is touching. And for total, uncompromised visibility, TCP dump lets you capture live, packet-level network traffic right from the command line.
But what if the attacker isn't active this very second? Well, that is exactly where logs come in. Logs are basically the system's story. We can comb through them to see exactly where attackers left their footprints. The auth.log tracks all authentication events. This is exactly where you're going to spot those massive spikes in failed logins that scream brute force attack. The syslog records general system activity, which makes it the absolute best place to hunt for unexpected scheduled tasks, those cron jobs you definitely didn't create. And the web server's access.log? That's where you'll find the telltale signs of SQL injection attempts or directory traversal scans.
Part 5. The Defender's Checklist.
All right, let's turn all of these foundational concepts into real, actionable defense strategies. The true superpower of mastering Linux is that when you know exactly what legitimate usage looks like, the anomalies just jump right out at you. Here are 5 major attacker patterns you absolutely have to recognize. Number 1, like we talked about, executables dropped in that world-writable temp directory. Number 2, persistence created via malicious cron jobs that just constantly re-download malware. Number 3, hidden users with a UID of 0. Listen, if an account has UID 0 and it isn't root, that is a backdoor for sure. Number 4, suspiciously cleared or totally empty log files. That's an attacker trying to clean up after they've compromised you. And finally, malicious additions to a user's bash RC file, which ensures malware runs the exact second they log in. And that brings us to the ultimate payoff, the 8-command security baseline. If you run these 8 commands, you will instantly get a powerful first-pass security assessment on pretty much any Linux machine. You're checking for those vulnerable SUID binaries, verifying open network ports, reviewing exactly who has shell access, auditing scheduled tasks, finding recently modified files, grepping for failed logins, checking live processes, and hunting for random executables in /temp. This isn't just theory and it's not buzzwords. This is real, actionable incident response straight from the terminal. By mastering these concepts and commands, you've completely transformed how you interact with the core infrastructure of the internet. You aren't avoiding the terminal anymore. You are commanding it. But I want to leave you with one final provocative thought. You can now defend the Linux substrate, the operating system that literally runs the world's servers. But are you prepared for what runs the world's enterprises? Because while Linux is the backbone, Windows and Active Directory remain the single most attacked piece of infrastructure on the planet.
Welcome to The Explainer. Today, we're going to look at your computer in a completely different way. We aren't just, looking at software here. We're going to treat the Windows operating system like a heavily guarded fortress. And over the course of this Explainer, we'll break down exactly how that fortress works, and honestly, more importantly, how attackers blueprint their way inside. So let's dive right in. What if I told you that 80% of successful breaches happen, well, not because of some incredibly complex, mind-bending zero-day exploit, but because attackers just exploit fundamental OS-level vulnerabilities? It literally all comes down to a concept called privilege escalation. They find a tiny crack in the foundation, and they pry it wide open. That reality brilliantly illustrates why you just can't buy your way out of this problem. I mean, I've seen organizations spend millions on fancy firewalls and endpoint detection, but then they have a system running where a group like everyone has write access to a critical folder like System32. Firewalls absolutely cannot fix architectural failures. If the blueprint is flawed, the fortress falls. So here's our roadmap for today. We'll quickly cover privilege rings, take a look inside the kernel, talk about securing the boot, examine systems and services, and finally, look at defending the fortress. Let's start with the foundation. Section 1, Privilege Rings, the Fortress Rules. Okay, so everything in Windows security essentially comes down to this one fundamental concept. Modern CPUs have hardware-enforced privilege levels. Think of them like super strict security clearances in a top-secret facility. There are two main clearances you really need to know about. On one side, we've got Ring 0, which is also known as kernel mode. This is the absolute highest privilege level. Code running here has unrestricted total God mode power. It can execute any instruction, access literally any memory, and talk directly to any piece of hardware. If an attacker gets in here, game over. They own the entire machine. On the other side, we have Ring 3, or user mode. This one is highly restricted, and it's where your normal, everyday applications run. Things like Chrome, Word, or Notepad. So the real crucial question here is, how does a restricted app in Ring 3 actually do anything useful? Well, it has to ask for permission. Let's say you want your browser to read a file, or, open a network connection. Your app has to make a formal request to the kernel, which is called a syscall. The CPU literally has to switch context entirely. It saves where it was, changes its privilege level, goes down to the kernel to verify if you have the right permissions, does the action, and then finally returns you to Ring 3. And this massive, heavy context switch, it's happening thousands of times every single second you use your computer. Section 2, Inside the Kernel, the Control Room. All right, we're stepping out of the restricted public areas now and entering the inner vault, the true control room of the operating system, the Windows kernel. The actual brain of this control room is a file called entoscarnel.exe. It lives right in your System32 folder, and surprisingly, it's pretty small, only about 10 megabytes. But do not let its size fool you. Once the bootloader loads this tiny file into memory, it runs entirely in Ring 0. From that exact moment on, it holds absolute unrestricted power over your entire computer. Now, what's truly staggering is the sheer weight of what this 10 megabyte file actually has to handle. Basically, it has 4 critical responsibilities. First up, memory management. It juggles all your RAM, creating virtual memory and isolating processes so that, hey, if one app crashes, it doesn't take down your whole system. Second, process management. It gives every running application an access token that dictates your exact privileges. Third is interrupt handling, meaning it manages every single keyboard press or network packet pinging your hardware. And finally, object management, which brings us to a core philosophy of Windows. And it's a big one. Everything is an object. A file? Object. A process? Object. Those access tokens we just mentioned? Yep, objects. And every single object has an access control list, or an ACL, attached to it. The kernel acts essentially like a very, very strict bouncer. Whenever you try to touch an object, the kernel checks your access token against that object's ACL to see if you have the right permissions. Match, you're in. No match, access denied. Right below the kernel sits the executive layer, which handles things like file systems and I/O management. But here is the major security catch we need to talk about. Device drivers also run here in Ring 0. Why? Well, because a graphics card or a network driver needs to talk to the physical hardware directly. But man, a buggy, poorly coded third-party driver running in Ring 0, that is a massive vulnerability. In fact, it's one of the most common vectors attackers use for privilege escalation. And hey, we really can't talk about critical processes without mentioning csrss.exe. This is the client/server runtime subsystem. Now, even though this actually runs in user mode, it's absolutely critical because it routes your window graphics and your keyboard inputs. If an attacker manages to inject malicious code into the specific process, they gain some seriously dangerous capabilities over exactly what you see and what you type. Section 3. Securing the boot, building the vault. But wait, how do we build this fortress safely in the very first place? The boot process itself is actually a major attack surface. Before the operating system even fully turns on, attackers are already trying to get in. It all starts with UFEI. Modern systems don't really use the old-school BIOS anymore. They use UFEI, which stands for Unified Extensible Firmware Interface. You can think of UEFI as a mini operating system that runs before Windows even boots. Its job is to initialize your hardware, check for viruses, and then finally launch the Windows bootloader. Alongside UEFI, you likely have a TPM, a Trusted Platform Module. Now, this isn't software. It's a physical, tamper-resistant hardware security chip soldered directly onto your motherboard. The TPM has some incredibly critical jobs. It stores your encryption keys for things like BitLocker, it verifies the integrity of the boot chain, and it seals data so that it physically cannot be extracted if, say, someone steals your laptop. Working hand in hand with that hardware is a feature called Secure Boot. Secure Boot ensures that the bootloader has a valid cryptographic signature. If malware has tampered with the bootloader in any way, the signature breaks, and the system just flat out refuses to boot. This is for sure our absolute best defense against bootkits, which are incredibly devastating pieces of malware that try to load before Windows, specifically aiming to secure that God mode Ring 0 access before your antivirus even has a chance to wake up. So, this secure boot chain ends up looking something like this timeline. At T+0 seconds, you press power and the firmware runs. At T+1, UEFI initializes the hardware. T+2, secure boot mathematically verifies the boot manager. T+3, the boot manager verifies our kernel, entostkernel.exe. T+4, the kernel loads and system services start. And finally, around T+5, your user session begins. This chronological chain is what we call a measured boot, where literally every single step cryptographically verifies the integrity of the very next step. It's like a giant chain of trust. Section 4, Subsystems and Services, the Automated Guards. Okay, so once the vault is built and the OS is running, we're outside the inner vault now. This is where the operating system actually does its useful day-to-day work for you. Windows relies heavily on subsystems for this. The main one you interact with is the Win32 API, which handles all the visible stuff: graphics, Windows, user input. But Windows has evolved wildly over the years. It actually now even includes WSL2, the Windows subsystem for Linux, which literally runs an actual native Linux kernel right inside of Windows. Pretty wild, right? Alongside subsystems, we have system services. These are long-running processes that just quietly operate in the background. Things like SQL Server, the Print Spooler, or Windows Update. What you really need to know as a security professional is that a lot of these critical background services run as system, which is the absolute highest privilege user account available on the entire machine. And that right there brings us to the ultimate threat path. Let's trace how a hack actually happens in this scenario. Step 1. A background service is happily running with those God-tier system privileges. Step 2. An attacker finds a simple flaw, say a directory traversal vulnerability in that service. Step 3. They exploit it to overwrite a legitimate file with their own malicious code. Step 4. The service gets restarted. Step 5. The service blindly runs the new malicious code, and because the service has system privileges, the attacker's code inherits those exact same privileges. Bam! They now completely own the machine. Section 5. Defending the Fortress. Understanding this architecture isn't just about, passing a certification exam. It is literally the only way to accurately map an organization's threat model. You absolutely have to know where the automated guards are and where the vault doors are in order to defend them. So I want to leave you with an immediate practical takeaway today. When we're done here, open up PowerShell on your machine as an administrator and type this exact command: get service where object s.status equals running. Take a really close look at the list of active services currently operating on your own fortress. Look at those services and ask yourself this critical, provocative question. Why is that service running as system? I mean, does it really need to be? Because if that specific service gets compromised tomorrow, your entire fortress falls. Critically evaluating configurations exactly like this is how you stop the next major breach. Welcome to the Explainer. We spend literally millions of dollars and countless hours obsessing over sophisticated malware, state-sponsored actors, and those terrifying zero-day exploits. We build these massive, impenetrable firewalls around our networks. But the grim reality? Infrastructure security is often way simpler and, frankly, way more preventable. We're talking about bad file permissions. It's exactly like building a billion-dollar fortress, locking the vault, and then just leaving the keys dangling in the lock on the inside. If an attacker gets past your perimeter, they don't need explosives. They just turn the key. Let's look at a terrifying real-world example from 2023. A pen tester was hired to assess the defenses of a major healthcare provider. Now, this wasn't some sprawling, multi-week campaign. No way. They took over the entire network in under 4 hours. Zero sophisticated exploits were used, zero days. They didn't even need any fancy social engineering. Instead, they literally just stumbled upon a single, misconfigured file hiding in plain sight. It held administrative credentials, and because the permissions were bad, anyone on the network could read it. They copied the credentials, and boom, game over. So here's a number that should absolutely change how we allocate our security budgets. 80%. The Center for Internet Security estimates that a staggering 80% of privilege escalation attacks stem purely from bad permissions. Not advanced malware, bad permissions. We buy these crazy expensive intrusion detection systems, but completely ignore the basic access controls baked right into our operating systems. Permissions aren't just some boring compliance checkbox to satisfy an auditor. They are the absolute bedrock of your access control. Today, we're going to tear down the illusion of security and actually fix how we protect our data. All right, here is our roadmap for today. First, we'll cover the anatomy of file systems. Second, we'll decode OS file permissions. Third, we'll walk through real-world attack paths. And finally, we'll break down the least privileged solution. Starting off with Section 1, Anatomy of File Systems. When we compare modern file systems, we see that Linux's ext4, Windows NTFS, and Mac's APFS all come equipped with these really robust, complex permission models. They're built to keep users separated and data secure. But then there's FAT32. Honestly, FAT32 is basically the Wild West of file systems. It has absolutely zero permission architecture built into it. None. If you plug a FAT32 drive into a machine, or heaven forbid, format a server partition with it, literally anyone who can reach that drive can read, modify, or delete the files. Using it for sensitive corporate data is just a total disaster waiting to happen. Now, forensic investigators rely heavily on 3 key timestamps when auditing a breach. Every file has an access time, a modify time, and a change time. And here's why this matters to you. Attackers know exactly how to manipulate these. If a hacker installs a backdoor, they'll use simple terminal commands to fake the modify time, making the file look like it hasn't been touched in years, just to cover their tracks. But C-time is different. C-time records when the metadata itself, like the permissions or ownership, was altered. And it's the ultimate forensic silver bullet. Why? Because you literally cannot fake it without high-level root access. It is your absolute source of truth. Moving right along to Section 2, Decoding OS File Permissions. Let's decode a Linux permission string. Kind of like reading a secret message. See that string on the left? That very first dash just tells us it's a regular file. Then we have 3 distinct chunks. The RW/ means the owner of the file, in this case root, can read and write to it. The RR/ means the group assigned to the file can only read it. And those final 3 dashes? Man, that is the most beautiful sight in security. It means everyone else on the system has absolutely zero access, period. This is standard Linux discretionary access control in a nutshell. But then we have special permission bits, and the SUID bit is a massive target for hackers. Think of SUID like handing out a temporary all-access VIP badge to a regular employee. If a custom binary is owned by root and has that SUID bit flipped on, anyone running that program temporarily acts with full root privileges while it executes. So if that program has a bug or can be manipulated in any way, the attacker leverages that VIP badge to take permanent control of the machine. It's literally a golden ticket for privilege escalation. Shifting gears to Windows, NTFS offers immense granularity compared to that blocky, simple Linux model we just talked about. Instead of just owner, group, and others, Windows uses complex access control lists, or ACLs. This architecture gives admins an incredible amount of power to say, hey, exactly this user can read this file on a Tuesday. But as we know, complexity breeds vulnerability. With all that power comes endless opportunities for catastrophic mistakes. When you've got hundreds of intersecting groups and nested folders, figuring out who actually has access to what gets incredibly difficult. And because of that complexity, granting full control in Windows is essentially pushing the nuclear button. In NTFS, read is your baseline. Stepping up to modify lets a user delete and write, but it importantly stops short of letting them change ownership. Full control totally shatters that boundary. It lets a user change permissions and take complete ownership of the file or directory. If an attacker compromises an account that happens to have full control over a sensitive network segment, they effectively own that whole segment. They can even lock your own admins out. This permission has to be heavily restricted. Windows environments also hide some pretty nasty traps, with inheritance being the biggest offender. Imagine an admin sets a root folder to everyone read, just to temporarily troubleshoot a bug. If they forget to change it back,
Every single subfolder and file created inside that directory permanently inherits at open access. Another huge blind spot is alternate data streams, or ADS. It's this fascinating, almost spy-like feature where files can have hidden data streams attached to them. Sophisticated malware actually uses ADS to invisibly staple its payload to a totally normal-looking text file, hiding completely out of sight.
All right, Section 3, Real-World Attack Paths. Let's see this in action. Imagine an admin leaves a web app config file set to 644, meaning it's world-readable by anyone on the server. Inside that file, a hard-coded database password sitting in plain text. So a low-level attacker just reads the file, copies the password, logs into the database, and quietly walks out with millions of rows of customer data. The fix for this kill chain is painfully simple. Config files with credentials must be locked down to 600, read and write for the owner only, and absolutely nothing for anyone else. Here's another one, a misconfigured cron job, which is basically letting your system hack itself on a schedule. If a nightly backup script runs as root but is left world writable, an attacker doesn't need to spend weeks cracking the root password. No way. They just open your script, add one line of malicious code, like granting their own account unrestricted sudo access, and wait. When the clock strikes midnight, the system dutifully executes the attacker's newly added code with root privileges. They instantly gain passwordless root access entirely by weaponizing your own automation. And it's these everyday mistakes that lead to total corporate compromise. A classic example? The Windows network share granted everyone full control during a chaotic Friday server migration. The IT team says, "Oh, we'll fix it Monday," but they forget. Months later, an attacker drinking your free lobby coffee on the guest Wi-Fi just maps the drive and downloads your financials with zero authentication. Or over in Linux, a home directory left open lets any user read an admin's bash history, easily scooping up plaintext passwords they accidentally typed right into the commands line. Finally, Section 4, the least privileged solution. So how do we fix this? You need the right tools, and standard find commands are literally your night vision goggles for spotting hidden threats. Running a search for files with the SUID bit set or identifying every world-writable file instantly illuminates your attack surface. If you run that first command and spot a weird binary hiding in a temp folder with the SUID bit flipped on, yeah, you are very likely looking at an active intrusion. And aside from very specific system folders, your list of world-writable files should be totally empty. If it's not, your front doors are wide open. Over on Windows, PowerShell is absolutely vital for auditing these sprawling networks. By piping get SMB share into get SMB share access, admins get an instant, crystal clear view of exactly who has access to what, easily exposing those terrifying everyone permissions. But wait, locking the doors isn't enough. You've got to combine this with audit poll to ensure Windows is actually logging access attempts. Having locks is great, but without access auditing, you have no security cameras. If someone is jiggling your door handles, you won't know until it's way too late. This brings us to the golden rules of system administration. Number 1, a complete ban on chmod 777. This is the YOLO command of Linux. Sure, it instantly grants everyone full access and fixes your permission-denied error, but it fundamentally destroys your security posture. Just don't do it. Next, keep your SSH keys locked down tight to 600. Ensure user home directories are strictly 700 so employees can't snoop on each other. And rigorously, aggressively, purge the everyone group from every single Windows share on your network. Everything we've talked about today really boils down to one unifying philosophy, the principle of least privilege. It demands that every user, process, and service has exactly the permissions they need to do their job, and absolutely nothing more. We shouldn't view this as a restriction. It's a protective boundary. We violate this constantly because granting full control is just so fast and convenient, right? While mapping out exact permissions takes actual work. But organizations that pick speed over security inevitably pay for it with catastrophic data breaches. As we wrap up this explainer, I want you to ask yourself a question. The next time you're tempted to grant full control just to make a pesky error message go away, are you actually solving a problem, or are you just handing the keys to your kingdom to a stranger in the dark? Your job isn't to make access perfectly frictionless. Your job is to make least privilege the default non-negotiable setting. Okay, let's jump right into this explainer where we are going to demystify exactly how attackers take basic, limited access and completely transform it into total, unrestricted network destruction. Seriously, if you've ever wondered what actually happens between that initial click on a bad phishing email and a full-blown ransomware deployment, you are absolutely in the right place. We're going to look right under the hood of Windows privilege escalation. Right off the bat, here is a statistic that should honestly keep you up at night. 90% of successful breaches involve privilege escalation. You know, organizations spend millions of dollars building these massive digital walls, firewalls, strict email filtering, expensive endpoint protection, all trying to stop attackers from getting that initial foothold. But the crazy thing is, they often completely neglect what happens after an attacker actually sneaks past the perimeter. Because practically speaking, most attacks follow this exact three-step chain. And this brilliantly highlights a huge misconception in cybersecurity. When someone clicks a phishing link, the malware usually just runs as that specific employee. They're a standard user with limited access, right? That is not the end of the world. The real nightmare kicks off at step 2. That's when the malware actively hunts for a vulnerability in the operating system, or maybe just a misconfigured service. It exploits it, and boom, it escalates right to step 3, full compromise. So today, we're going to break down this exact process into 5 parts. The privilege escalation threat, Windows accounts and tokens, 5 privilege escalation vectors, hunting vulnerabilities with WinPs, and finally, defending and detecting attacks. Let's get into it.
Starting off with Section 1, the privilege escalation threat.
So what is the ultimate goal here? For an attacker on a Windows machine, it's all about achieving system access. This is it, the absolute highest level of authority you can get. Once an attacker gets system access, they own everything locally. They can mess with the Windows registry, they can completely kill your antivirus processes, and most dangerously, they can pull network credentials right out of a critical process called lsass.exe. And once they have those, they can seamlessly move laterally to other machines, plant persistent backdoors, steal your sensitive data, or just deploy organization-wide ransomware. Moving right along to Section 2, Windows accounts and tokens. Before we talk about how attackers break the rules, we need to know what the rules actually are. When you log into a Windows machine, the OS hands you an access token. This token is totally critical because it dictates every single action you're allowed to perform. Think of it kind of like your digital VIP badge. Inside this token is your unique security identifier, or SID. It also holds your group memberships, so maybe you're in the developers group or HR. It lists your system-wide privileges, and it assigns you an integrity level, which scopes down exactly which processes you can even interact with. Now, here's a crucial distinction that literally trips everyone up: permissions versus privileges. They sound the same, but they are very different. Permissions dictate what you can do to a highly specific resource, like, do you have permission to read a specific Word document on the C drive? Privileges, on the other hand, are system-wide capabilities. If you hold a privilege called cdebug privilege, you have the global power to attach a debugger to any running process on the machine, read its memory, and inject code into it. So just remember, privileges are global, permissions are specific.
All right, let's dive into Section 3, 5 privilege escalation vectors.
You know, a lot of people just assume hackers are always using these ultra-advanced, impossible-to-stop zero-day kernel exploits. But look at this. Unpatched kernel exploits only make up about 15% of the pie. A massive 75% of successful privilege escalations come from just 2 vectors: unquoted service paths and weak file permissions. Basic everyday misconfigurations actually make up the vast majority of real-world escalation paths. Let's look at the absolute biggest offender: unquoted service paths. It sounds technical, but the concept is surprisingly simple. When a service is configured to run an executable, but the path to that executable has spaces in it and isn't wrapped in quotation marks, Windows gets confused. It treats those spaces as delimiters. So if your path is c/programfiles/myapplications/service.exe, Windows first just looks for a file called program.exe directly in the C drive. An attacker can just create a malicious executable, literally name it program.exe, drop it right there in the root directory, and wait for a reboot. When the system restarts, Windows executes the attacker's file as system. No way, right? But it works. Then we have the second massive vector: weak file permissions. Imagine a totally legitimate service running as system. If defenders run a quick PowerShell ICALS check on that services folder and see that the general users group has write access, which is what that W means right there, that is a critical flaw. The attacker doesn't even need to be clever here. They just delete the legitimate executable, paste their own malicious file in its place, and restart the service. Instantly, their code is running as system. The rest of the vectors follow a pretty similar theme. Unpatched kernel exploits trigger memory bugs deep down in the operating system's Ring 0 code. Dangerous privileges happen when a standard user is accidentally granted something crazy like sdebug privilege, which basically hands them the keys to dump credentials straight out of memory. And DLL hijacking? That's when a high-privileged service just blindly loads a malicious code library from a directory that literally anyone can write to. The absolute crucial takeaway here is that for every single one of these vectors, a process running with high privileges doing something insecure is always the root cause. Which brings us nicely to Section 4, hunting vulnerabilities with WinPS. So how do we actually find these things in the real world? Interestingly, attackers and defenders use the exact same automated enumeration scripts to scan for these misconfigurations. One of the undisputed favorites is called WinPs. You just run this single executable, and it scans the entire machine, spitting out a super detailed report. It knows exactly what an unquoted service path looks like. It'll scan the services, see that missing quote mark and those spaces, and flag it in bright red text as vulnerable. It points out exactly where the system is weak. WinPS also checks your active user's access token. If it sees that a standard user holds a dangerous capability like said debug privilege, it flags it as exploitable. If you're a defender running an audit and you see this pop up, it's a massive red flag. It literally means the account you're auditing right now can escalate to system immediately. They don't need to drop files, they don't need to wait for a reboot, they can just attach to a system process and completely take over. Let's wrap things up with Section 5, defending and detecting attacks. Here is the harsh reality. You simply cannot patch your way out of this problem. Remember, 75% of these exploits aren't about missing patches, they're misconfigurations. You've got to implement a robust, multi-layered defense strategy. Layer 1 is foundational, least privilege. Users should be standard users, period. Then you harden your services by making sure you're rigidly quoting all executable paths and locking down directory permissions. You audit those user privileges, you strictly enforce OS updates, and finally, you monitor your endpoints aggressively. Because what does that monitoring layer actually look like in practice? Standard network firewalls are practically blind to this stuff because privilege escalation happens entirely locally, deep inside the Windows kernel. You need endpoint visibility. With the right tools, like Sysmon or a solid EDR solution, blue teams can spot the attack as it's developing. When an attacker creates that malicious program.exe file on the C drive, that triggers a file creation event. Your tool should catch it at step 1, neutralizing the threat way before the service ever gets a chance to reboot and run the code. Ultimately, privilege escalation is that hidden bridge turning a minor, annoying phishing incident into a total, catastrophic network compromise. And the craziest part? Most of these breaches are caused by simple oversights. A missing quote mark, a folder that's a bit too permissive. We're not talking about advanced 0 days here. So take these actionable steps today, run your audits, and make absolutely sure you aren't leaving the front door wide open. Ask yourself right now, is your network truly secure, or are you just one misconfigured service away from a disaster? Listen, right now, somewhere in your organization, there's a very good chance you've got a container running with root privileges. A container built from an image absolutely no one reviewed, running code that could be easily escaped. Welcome to this explainer. If you're in cloud security or maybe you're a DevSecOps engineer, you're going to want to lean in for this one. We are about to dive into what is easily the most critically misunderstood and honestly most exploited attack surface in modern infrastructure: containers. Okay, here's a stat that literally blew my mind when I first saw it. 73% of container images in public registries have at least one critical vulnerability. 73%. That's basically 3 out of 4. What that means is if you're using container technology at scale, which, let's face it, you probably are, you are almost certainly running vulnerable code right now without even knowing it.
So here's our roadmap to take back control. First up, the container security blind spot. Second, deconstructing Docker containers. Third, Kubernetes architecture and risks. Fourth, the top 5 container vulnerabilities. And finally, your blueprint for hardening. Let's get into it.
Part 1. The container security blind spot. Containers aren't VMs. All right, we've got to clear up a massive mental roadblock right off the bat. A lot of organizations are taking these revolutionary, lightning-fast containers and incorrectly treating them exactly like traditional 20-year-old virtual machines. And from a security perspective, that is a huge mistake. With a traditional VM, you're getting complete hardware-level separation. Every single VM gets its own dedicated operating system and its own entirely separate kernel. If one VM gets compromised, the others are relatively safe. But containers, they rely purely on OS-level separation and process-level isolation. The absolutely crucial difference you need to remember is that containers all share the host kernel. They aren't VMs, they're really just lightweight processes with isolated file systems. Because folks don't fully grasp that shared architecture, we're seeing massive risk management failures. According to data from Aqua Security, almost half, 46% to be exact, of all container vulnerabilities out there are categorized as high or critical severity. Treating containers like VMs creates this terrifying blind spot, leaving a huge chunk of all deployments critically exposed. Moving on to part 2, deconstructing Docker containers, understanding the layers. Think of a Docker image like a read-only template, basically a blueprint built in distinct layers. You start at the bottom with a base OS layer, then you stack on your application layer, your configuration layer, and finally your dependencies. So here is the kicker. If your very first base layer, say some outdated Ubuntu image from 6 years ago, has a known vulnerability, every single container you ever build on top of that image automatically inherits that exact same vulnerability. Now, when you actually take that layered image and spin up a container, Docker relies on this clever little magic trick in the Linux kernel called namespaces to make the processes think they're in their own private world. The PID namespace tricks the container into thinking it's the only process running. The network namespace gives it its own IP address. The mount namespace gives it an isolated view of the file system. It feels like real isolation, but honestly, it's just an illusion. They're merely isolated views of the exact same underlying host. And that brings us to the terrifying reality of this shared architecture. All those containers, relying on those clever namespaces, still funnel down to share one single host kernel. Container isolation is truly only as good as the host kernel itself. If an attacker finds a kernel bug or a container escape vulnerability, they don't just compromise that one container. Nope. They break out completely and instantly own the entire host. Game over. Part 3. Kubernetes architecture and risks. The risk multiplier. So, what happens when we scale those containers up? Kubernetes. It is absolutely incredible at orchestrating massive deployments. But to understand its risks, you have to look at its two main parts. You've got the control plane, which is the brain of the operation, handling API requests, scheduling workloads, and storing all your sensitive data in a database called etcd. Then you have the worker nodes, the muscles that run the actual container runtimes and workloads. The golden rule here is simple. If someone compromises the control plane, the brain, they've just been handed the keys to your entire cluster. But here's the crazy part. Out in the wild, almost every Kubernetes cluster tested has highly exploitable default insecure settings right out of the box. Kubernetes uses a default allow networking policy, meaning any pod can talk to any other pod. Often, there are 0 role-based access control restrictions. Secrets in etcd are basically stored in plain text as simple base64 encoded strings, which, by the way, is not encryption. We routinely see pods running as root and mounting the host file system. Any single one of these is exploitable, and most clusters actually have all of them. Part 4. The top 5 container vulnerabilities causing real-world breaches. These are the 5 specific misconfigurations actually causing breaches right now. Number 1, without a doubt, is running containers as root. If you don't explicitly specify a user, your application defaults to root, making it the biggest privilege problem across the industry. After that, we have vulnerable, outdated base images, storing database passwords as secrets in plain environment variables, container escape vulnerabilities like the runc escape, and finally, those deeply misconfigured Kubernetes defaults we just talked about. Let's look at how a malicious actor actually chains these exact 5 vulnerabilities together in practice. It's like a devastating domino effect. Step 1, the attacker finds a known vulnerability in an outdated base image you're running. Step 2, they exploit it to get code execution. And because you left the default settings, boom, they immediately get root access inside the container. Step 3, using a kernel exploit, they escape the container entirely and land squarely on your host. Step 4, now that they're on the host, they read the unencrypted database to steal your Kubernetes secrets and API credentials. And step 5, they use those credentials to compromise your entire infrastructure. And if you're sitting there thinking these attack chains are purely theoretical paranoia, let's look at the devastating Capital One breach back in 2019. The initial intrusion was just a misconfigured web application firewall in AWS. But how did it escalate to such a catastrophic level? Through a container escape. That single escape allowed access to the Kubernetes metadata service, which led to stolen IAM credentials, which gave them access to the database, resulting in the theft of 100 million customer records. One misconfiguration led to the whole shebang being compromised. Part 5. The blueprint for hardening, your actionable defense plan. So take a breath. How do we actually prevent a breach like this from happening to you? Look, you don't need to implement perfect security on day 1. We want to frame your immediate next steps around pure business value, focusing on high-impact, low-effort wins. Adding just 2 lines of configuration to your Docker file to run as non-root, that is incredibly low effort, but it instantly prevents countless privilege escalation attacks. Adding one single command to scan images in your CI/CD pipeline finds vulnerabilities before they ever reach deployment. And swapping out base images is a super easy way to dramatically shrink your attack surface.
So, here is your concrete homework for this week. First, audit and scan your current images. Use free tools like Trivy, Gripe, or Snyk. You absolutely have to know what you're running. Second, switch to minimal base images. Moving from a bloated 75 megabyte Ubuntu image to a 5 megabyte Alpine image instantly reduces the number of vulnerable packages you're exposing. And third, change your Kubernetes default networking. Drop the allow all approach and set a deny all ingress policy to shut down lateral movement.
Once you've got those quick wins, here is your roadmap for the rest of the month. Stop putting your secrets in environment variables. Implement a proper external vault like HashiCorp. Enforce pod security standards to strictly block host network access and privilege mode. Clean up your permissions by enforcing least privilege RBAC. And start signing the images you build with tools like Cosign. Remember, incremental progress beats paralysis every single time, and building secure containers is the absolute foundation of all cloud security.
Which leaves me with a pretty serious question I want you to take back to your team. How many of these exact vulnerabilities are sitting live in your cluster right now? Seriously, challenge yourself. Go run a vulnerability scanner on your own systems today. Audit your configurations, find out what's running as root, and start implementing these controls. If you get this right, you've literally solved half of your cloud security problems. Thanks for joining me for this explainer today. Now get out there, build some secure containers, and I'll catch you next time.